Hello, students. Let me talking about section 1.2 briefly here. We kind of went over a lot of this in class, but I do want to talk a little bit about one of the concepts that we mentioned, and I tried to emphasize, but I want to just kind of reiterate why it's so important. And it's the idea of kind of that reasoning. So when we see a sequence, for example, in class, I think I did 2, 4, and then did something like this, right? 2, then 4, then it just kept going. And the idea was we can't know for sure what the next term is unless we are told how this sequence continues. So for example, you might say, oh, no, Scott, I know how this continues. It goes 2, then 4, then 6, then 8, dot, 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 right? And you're just like, oh, it keeps going that way because you noticed that you're kind of adding 2 to each prior term. So add 2, add 2, add 2, add 2. That's perfect, of course. But someone else comes along and says, oh, no. I see it, Scott. Don't worry. You're actually multiplying by 2. Okay, so 2, 4, then 8, then 16, and then from there it just kind of keeps going. So this is a times 2 pattern, making it geometric, the first one being arithmetic. But somebody else says, no, Scott, hold on, I got this. What you did is, yes, you did add 2 to start, but then you're going to add 3, and then you're going to add 4, and then you're going to add 5. And so that keeps going. Okay? Totally different sequence, not geometric, not arithmetic, but there's nothing wrong with any of these sequences. They're all pretty nice. So as you're kind of looking at these, sometimes it's helpful to find patterns with common differences. And we talked about that in class. And if you found the common difference here, you'd see it was 2, then 3, then 4, then 5, and you say, ooh, this is not an arithmetic sequence because they're not all the same. But if you found the next difference, this is what's kind of cool about these patterns, is this one is common. So the second difference, if you will, is common. You could use that to kind of say, well, then the next one should be a 1, this would be a 6, and I could work my way up and say the next term would be 22, and so on. Okay. So sometimes the first difference isn't enough. It's not common. Take the second difference, see if that helps. Okay. All right. So again, the idea that from this I can get to any one of these guaranteed if there's no additional information, that is known as inductive reasoning. Okay. And inductive reasoning is not bad. We do it all the time. We just don't have necessarily the guarantee that it continues. And I think that's the part I want to make sure that I mention here. Inductive reasoning gives you a conjecture or a guess. In this case, a pretty educated guess. And again, all of your rationale, you have an explanation. That's great. But what you can see is there might be more explanations that also produce a viable outcome. So we want to be careful. So that's the idea here with inductive. Now, if we were doing something with what's known as deductive reasoning, we could prove, guarantee to someone that this is what happens. Let's take a look at how this would play itself out. So what I'm going to do is I'm going to take 3 consecutive numbers. I'm going to start with 3, 4, 5. Now, if I add these up, okay, so 3 plus 4 is 7, plus 5 is 12. Okay, that's 12. I want you to notice something here. I end up with 3 times that middle term. Okay. Let's pick a different one because maybe it's like, okay, I don't see that. Let's try 7 plus 8 plus 9. So 7 plus 8 plus 9. All right, so now let's see here. 9 plus 8 is 17, plus another 7 is 24. Okay, that's 24. You're like, oh, 24 turns out to be 3 times 8. Okay. Well, that seems pretty coincidental. Maybe let's go with bigger numbers, shall we? Let's do 93. 92, right? I'm just picking numbers randomly. 94. Okay, here's three consecutive numbers. Now, if I add those together, I'm going to need a little bit of help here, but let's see here. 90 plus 90 would be 180, plus another 90 would be 270, 275, 279. Okay, so 279. And if you take a look, 279 is 3 times 93. So the question is this always true? Is it always true? Now we've seen three examples, and you might say to yourself, well, I mean it, yeah, I think it is always true. So the question then is, can we demonstrate to others that it has to be always true? And if you're going to do that, you can't use individual examples like these. See, because all you did is showed that it works for these three. You would have to show it works for all groups of three consecutive natural numbers. So instead of just writing all of them out, because there's infinitely many and we'd never get there, what we try to do is instead we try to prove to someone that this is always the case. And when we try to prove something, we want to do it in general. So typically we would start with one of the numbers, doesn't matter. Okay, here we go. And we would generalize that number. So the numbers that I want to pick now are going to be like the number, let's see, if you like algebra, you could use X. If you want to pick just a number, maybe number starts with the letter N, so I would use N. But I'm going to choose A just because I feel good with that. So here's A. Okay, that's the first number. And because I want consecutive numbers, the next number, to get to the next number, I would add 1. So I would put A plus 1. Okay. And then to get to the last number, I just add 1 to the previous. So that would be A plus 2. Okay. And now we're going to do a little bit here with algebra. Again, prerequisite for the class, not a big deal. Not a big deal. A plus A plus A would get you 3A. And then I have a plus 1 and a plus 2, so that would be a plus 3, which is, if I now factor, it's now 3 times A plus 1. Well, let me change the color. Take a look over here. There's the middle term. And the sum of the three terms is always going to be 3 times the middle. So now it doesn't matter what number you put in here, as long as you add 1 to get the next one and you add 2 to get the third number, I promise you it will always equal 3 times the middle number, and this proof demonstrates why that has to be the case. So this reasoning over here is known as deductive. Okay, and with deductive reasoning, when you do it properly, the conclusion is going to always be the case. It's going to be true. Not so with inductive. Remember, with inductive, you could say, oh, I'm adding 2 to this, so that's how I get to the next term. Well, I mean, you might be right sometimes with inductive reasoning, but you also, there's a lot of other options out there. So we want to make sure if you don't know why something continues, you could say, I think it is this, but I'm using inductive reasoning, so I might not match with what someone else was thinking. Okay, let's see here. We went over arithmetic and geometric in class. We talked about figurate numbers, like the Wii bowling, if you remember that. Let's see here. So I don't know if there's too many that I'd want to go over from the homework. They're pretty standard when you're looking at those like exponents and stuff like that. Yeah, I'm not so sure I see anything there. Let's maybe we'll do a problem just to kind of see what it looks like. Doop, 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 doop. Let's take a look at 15. So 15 starts with a little box that looks like this with two squares. The next box looks like this. I'm going to do my best to draw. As long as your drawings are about as good as mine, you're going to be just fine in this class. All right? I think it kind of looks like this. Okay. There we go. Yep. Okay, so here's kind of the first term. Here's the second term. And then my third term. Third term, I have 1, 2, 3, 4 going up and down. And 2 going left and right. Is that correct? Okay, that matches. Okay. So, and this is one thing that I actually don't like, and I did convey this to the authors because I still believe there's more than one way to continue this pattern. And they said, no, the directions are pretty clear, but I still disagree with them. Notice the directions say, assume the following pattern with terms built of square tiles continues. So assume the pattern continues. Which pattern? So most of the time when they say that, they're looking for the most obvious pattern, but it is not the only pattern. So the most obvious pattern is that what you could do, at least as I see it, is right here, I could put one more tile kind of in the middle of this column. Okay, that would be this tile right here. Add that one in between those. Now I have 3. And then add in one additional tile on the lower left and one additional tile on the upper right. Okay. So if I come over here, now I would be saying, okay, this tile gets added, and then to the upper right, this tile gets added, and one to the lower left. Oops, get in there. And then one to the lower left right here. Okay, there we go. Okay, so what you can see is if we assume this is the pattern that they are referring to, then we would be adding one additional tile in the middle, one additional tile on each of the upper and lower sides. So that gives you 3 tiles that we'd be adding each time. Now, if you pick that up, to me, the quickest thing to do, so notice it does give you like an A, a B, and a C, right? A says how many square tiles are in the 7th figure? Okay, so it says 7th figure. Okay, and then part B says how many square tiles are in the nth figure? To me, it's almost easier to do part B first. Otherwise, you're under the impression that you have to draw it out to get to the 7th. And that's not what it says. It doesn't ask for that. Okay. So let's see here. So notice what I would do is, let's see here. Do we want to use Brooks technique? You could use Brooks technique if you want. All right, Brooke, you made the highlight reel. So here I have 2, then I have 5, then I have 8, dot, dot, dot. So if I turn that into just a sequence of numbers, 2, 5, 8, the next one is 11. And if you want to check, that is the next one that's actually shown in the book. That's what, 5 going up, and then 3 on each side. So 3, 3 is 6, plus 5 is 11. Okay. So if I want to use Brooks' technique, remember Brooks' technique from class, she said, okay, I see I'm going up 3 each time. So she wants to go backwards 1. And if you go backwards 1, you're going to be at -1. You know 3 is your common difference. So what you could write is that give me any term you want. It's just 3 times the term number, and then I take 1 away. So thank you for that one, Brooke. Let's see here. I guess I want to, maybe you could also do it a different way, right? So you could say to yourself, okay, wait, I'm going up by 3 every time. So it feels to me like my answer should include 3 times something, and then check it with that first term. The first term is 2. So if I plugged in a 1 here for 3, 3 times 1 would be 3. It's supposed to be 2, so I better take 1 away to make it work. So there's 2 different techniques you could use there. Or you could come over and say, oh, Scott, I've got a third technique. Is this okay? I'd say, well, it certainly could be. And you say, well, I start with 2, and then I add a bunch of 3s, but to get from 2 to 5, I'd add 1 3. To get from 5 to 8, I'd add 1 3. But that'd be 2 total, but that's the third term, and that's why we always have the n minus 1. If you distribute, and then simplify, so 3n and a plus 2 and a minus 3 would get you a minus 1. So I want you to see that they are all the same at the end of the day. So that makes it easier. When somebody says, what's the 7th term? You could just come up and put in a 7 and take 1 away. 21 minus 1 is 20. So done. There we go. And lastly, it says, if there is a figure that has exactly 449 square tiles, which one is it? Okay, so the number of tiles is now 449. So what I would say is 449 is equal to some number. And again, I'm not sure about this, but it could be the case. So let's do a little work. Let's add 1 to both sides. Get a little algebra here as we go. 3n, 450. Okay, so now I just divide by 3. Let me go up and write that down just so we can see it here. I'll divide by 3 and go back to my black color. This is going to be n, and over here I get 150. So is any one of these shapes that I make actually going to have 449 different tiles in it? And the answer is yes. The 150th term has, oh, that M is so horrible. The M is one term has 449 tiles. Okay. So that's the idea. And again, as you look through it, you may have geometric, you might have arithmetic, but the goal is think through, how can I create that general sequence, that general rule? If you have the rule, like we did here in B, then A and C and everything else come along pretty quick. All right. That is it for the 1.2 piece. I emphasized something that I might have missed in class. I'll do a little mathematical connections 1 for 1.2, and then we'll keep on trucking with the rest of it. All right, off you go.